All right, 5.2, day number 2. The goals of today are to be able to use Riemann sum, left, right, midpoint, and trapezoid with numerical data and tables, aka tables. Analyze the difference between distance as well as displacement. All right, so example number 1 is from the 2003 exam. All these problems we're going to do here are in the homework packet, I believe. Yep. So it looks like the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable function and strictly increasing. Those could come into play later in our problem. The graph of R and the table of the selected values of R of t for the time interval from 0 to 90 are shown above. So R of t, right, is gallons per minute, or our rate. And this is the graph of R of t. So if we want to, like it says here in part C, approximate the value of the integral from 0 to 90. Now, I believe this might be the first time you're introduced to definite as opposed to indefinite. Here's an indefinite integral, which is the area under the curve with no constraints on it, right? No restrictions. But this would be the area of the curve from 0 to 90. All right, so this is a definite integral, and this is an indefinite integral. Indefinite and definite. So approximate the value of 0 to 90 of R of t dt, the integral using a left Riemann sum with the 5 subintervals indicated by the data in the table. So here's subinterval 1, here's subinterval 2, 3, oh, I missed something there. Okay, writing too large. Here's subinterval 1, 2, 3, 4, oh gosh, 2, 3, 4, 5. Now notice that the width of these subintervals change. So the width of the first one is 30. Okay, so the width of my first subinterval is 30. We're doing a left Riemann sum, so we're going to get an area. The width of my next one is 10. So it's a smaller subinterval, left-hand sum. Then I have another interval of 10. Okay, we'll do an estimation using this left Riemann sum again. And it looks like 20 followed by another 20. So I get that followed by that. So what we're going to do is find the area of these 5 rectangles, these 5 subintervals, and we're going to add them all up. So the area of the first one, base is 30, height is 20, so 3 times 6, or 3 times 2 is 6, so that would be 600. The area of the second subinterval would be 10 by 30, which is 300. The area of the third subinterval would be 10 by 40, which would be 400. And on and on. So 20 by, oh gosh, is that 55? 20 by 55 would be 1100, and 20 by 65, 20 would be 1300, I believe. Okay, so let's just review how I got these values. To find the area, I'm just taking base times height, which is width, right? So 30 times 20. I'm going to add all of these areas up. So I had 30 by 20. I had 10 by 30. I had 10 by 40. And then I had 20 by 55. And I had 20 by 65. All right, so let's add all these values up. 600 plus 300 plus 400 plus 1100 plus 1300. Okay, so what is this telling us? All right, this numerical approximation is telling us how many gallons of fuel, right? How many gallons have been consumed from time 0 to 90 in those 90 minutes. Is it minutes? Yes, it is. So the number of gallons consumed during those 90 minutes would be, what is this? 1,300 plus 1,300 is 2,600. So how about 3,700 gallons? Okay, now it asks, is this numerical approximation less than the actual value? Well, let's look at the graph. Looks like I have a concave, well, it's an increasing function and a left-hand Riemann sum. So since it's an increasing function, since we have an increasing function r of t with a left Riemann approximation, then this would be an underestimate. I believe I have the key on the next page. Let's see how we did. Part C. Part C, 3,700 gallons. Yes, this approximation is less than the graph of R. Less than the graph of R is increasing in the interval. Because, I missed a word there, because. Okay, so we have the value of the left Riemann sum, which is 1 point. We have the less with a reason. So we said underestimate with a reason. Therefore, we get 2 out of 2 on that part of that problem. All right, let's try another one here. Given this data table, this is from 1999, the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r. So this is a rate again. So if we have a rate, or a table with rates, most likely we're going to be doing some kind of Riemann sum or integration. Right? The table above shows the rate as measured every 3 hours for a 24-hour period. Use a midpoint Riemann sum with 4 subdivisions of equal length to approximate the number of gallons that have flowed out of a pipe for those 24 hours. Okay, so this is going to require us to use a little bit different method here. First of all, midpoint, as well as it's not already separated into the correct number of subdivisions. So we want 4 equal subdivisions. Okay, so I'm going to go here 1, here subdivision 2, subdivision 3, subdivision 4. So what is the width of each of my subdivisions? Well, it'd be 6. All right, so I have a width of 6. Now with left Riemann sum, if I were to do the left Riemann sum, I would use this value. That would be my height. And this would be my base. All right, so I have a base in all cases. Because I'm using midpoint and forming rectangles, these will be all of my bases. If I use the left Riemann sum, right, then each of these would be my heights. Okay, because I'm not doing a left Riemann sum, let's say I was doing a right Riemann sum, then I would use each of these. I would shift it over to the other side and do a right Riemann sum. So for this interval right here, this would be the rightmost value on that interval, right? But I don't want to do a right Riemann sum, I want to do a midpoint. So now my height will be the value in the middle of that subinterval. Okay, so if you look at this as separate subintervals, right, I know my base and I know my height. Here's my subinterval, my midpoint height. Here's my subinterval, my midpoint height. And then, of course, my midpoint height. Okay? All right, so what we're going to do is we're going to multiply the base times the height, which is the midpoint of the subinterval, and add all those up. So for part A, I'm going to go off camera for a moment and write all these down. Okay, so check out what I did. I've approximated the area under the curve for this rate r of t from 0 to 24. And instead of multiplying 6 by 10.4 and 6 by 11.2 and 6 times 11.3 and 6 by 10.2, because they each have an equal base or an equal width of those subintervals, I can just add all those values up, all those rates up, and multiply them by 6. I get 258.6 gallons. Using correct units, explain the meaning of your answer in terms of water flow. So I would say that over the course of those 24 hours, is it hours or minutes? What is it? Yeah, over the course of those 24 hours, approximately 258.6 gallons of water flowed out of that pipe. All right, so let's look at part B. Is there some time t between 0 and 24 such that r of t has to equal 0? Justify your answer. Okay, I would say yes. And the reason I would say yes is because if I find the slope of the secant line on this interval, right, the slope of the secant line on this interval would equal r of 24 minus r of 0. That should be a 2. 24 minus r of 0 over 24 minus 0. Each of these, r of 24 and r of 0, are both equal to 9.6. So I take 9.6 minus 9.6 over 24 minus 0, which would be 0 over 24, which is 0. Therefore, by the mean value theorem, we are guaranteed, due to the fact that the secant line slope on that interval is 0, we are guaranteed that there will exist some t such that, what would that be? R prime of t has to equal 0. And that t, of course, let me say this, t will be between 24 and 0. So some t between 24 and 0 such that r prime of t has to equal 0. Okay, so let's check and see how we did on part B. All right, so it says yes. Okay, did we say yes? I don't know if we officially said yes. Let's say we did, seeing that we said that this would require, the mean value theorem would guarantee. So we did use the word guarantee. But since r of 0 equals r of 24, which is 9.6, the mean value theorem guarantees that there exists a t between 0 and 24 such that r prime of t equals 0. I'd say we're teetering on 2. I know what you probably think, well, it's really picky. We actually need to say yes. You have to answer the question. So I'd say we're teetering on a 2 on that portion of that question. All right, let's keep moving. All right, let's do one more. Johanna jogs along a straight path. It looks like, I would hope that's 40 minutes, right? Her velocity is given by a differentiable function v in the table above, where t is in minutes and v of t is measured in meters per minute. Okay, using correct units, explain the meaning of this integral. Okay, so first of all, let's analyze this table for a moment. What does this mean as opposed to, this, right? So a negative 220 just means that she's traveling in the opposite direction that she started. All right, so she starts off, she's jogging, let's say, to the east for, I don't know, somewhere up to potentially 24 minutes. She's jogging to the east, and then somewhere around 24 minutes. We don't know exactly when that would be. She turns around and jogs the opposite way. And then somewhere around 40 minutes, well, at 40 minutes, she's jogging east again. But we don't know when she changes from east to west and then back to east, right? So that negative velocity is just directional. So using correct units, explain the meaning of that definite integral. All right, so what would that mean? All right, so the integral from 0 to 40 of v of t, the absolute value of v of t, that's asking us to find all distances, right? And some of those distances, or if we use a Riemann sum, they might come out to be negative. Well, the negatives would negate some of the positives, and so then we get displacement. But what this is asking is it's asking for the total distance traveled, because there is some overlap in distance, not the displacement. So this is asking for total distance. All right, so using correct units, explain the meaning of this in the context of the problem. So what would that mean? Well, this would be the approximate total distance traveled if we were to use the Riemann sum method on the interval from t equals 0 to t equals 40. Okay, and the measurement of that would be, I believe, meters. Okay, so it asks for correct units, which would be meters, and an explanation, which we did. approximate the value of that using a right Riemann sum with the 4 subintervals indicated in the table. Okay, so they gave us nice subintervals. We're doing a right Riemann sum. So it looks like our base here is 12. Our base here is 8. Our base here is 4. Our base here is 16. A right Riemann sum would require us to use the right edge of each interval. So we would use that edge for the 12. We would use 240 with 8. We would use negative 220 with 4. And we use 150 with 16. So let's multiply those together. And let's do the absolute value. Okay, so the integral from 0 to 40 of the absolute value of v of t dt would mean that we're just going to take the absolute value of each of our velocities, okay, which only changes one of those from negative 220 to positive 220. Therefore, we've got 12 times 200 plus 8 times 240 plus 4 times 220 plus 16 times 150. I'm going to do a calculation off camera and we'll come back and look at the result. So after a quick calculation there, I see that the approximate distance traveled for Johanna was 7,600 meters. Now what if, just for a moment, what if we were looking for displacement and not total distance? Right? Then we would get 4,800. Right? I'd get 4,800 plus 1920 minus 880. Okay, so if that were a negative instead of a positive, what I would get for displacement would be approximately 5840. So what's the difference between these two? Well, displacement means how far from where they originally started, whereas distance means how far did they travel in total. So displacement would be a difference of just not taking the absolute value of v of t. This is displacement, which would be 5840, whereas this is distance when we talk absolute value. All right, let's see how we did. Let's move on to this next slide and check the key. Did we do it right? Yep, 7,600. Let's see how many points we got. Explanation. At the total distance Johanna jogs in meters over the interval, I'd give us a point there. It looks like the right Riemann sum set up. We've got that set up right, and then the approximation of 7,600 meters is also right on. All right, that I believe, oh, there's one more. Let's do one more. Okay, we've got a table. The function f is continuous on this closed interval 2 to 8 and has values that are given in the table above. Use the subintervals 2 to 5, 5 to 7, and 7 to 8. What is the trapezoidal approximation of the integral from 2 to 8? I'm just going to plot these, actually. I think that would probably be the easiest. X, f of x, to see it visually. Personally, that's how I like to do it. So we're going to go from 2 to 5. So we're not starting at 0. So 2 to 5. And we've got an f of x value of 10 at x equals 2. We've got an f of x value of 30 at x equals 5. Okay, so I got my first trapezoid there. What is f of 7? Okay, so up to 7. And f of 7 is 40. So I'll go up here to 40. Plot that. And then f of 8 is 20. Is 20. Okay, so let's find the area of these three trapezoids. We'll call that one number 1, number 2, and number 3. So let's estimate the integral from 2 to 8 of f of x dx. All of these areas will be positive, so we don't need to worry about any displacement issues. So let's go, first of all, Let's find the heights. The height here is 3. The height here is 2. The height here is 1. Okay, and then my bases are going to be determined by the f of x values. So the area of the first trapezoid will be 1/2 base 1 plus base 2 times the height, which is 3. The two heights are 10 and, is that 30? Yep, 10 plus 30. Okay, we're going to add that to the second trapezoid. So that'll be 1/2 base 1 plus base 2. That's 30 and 40. And the height, or the distance between those, is 2. Okay, I always like to see heights of 2 because that will cancel with the 1/2 out in front, which makes whole numbers much more likely. Okay, and then we've got 1/2. Our two bases are f of 7. F of 7 was 40. F of 8 is 20, and the distance between them, the height, is 1. I'm going to go off camera, simplify, and we'll see what we get. Okay, according to my trapezoidal Riemann sum in these three subintervals, I'm getting 160. There's no units attached, so it looks like my answer will be C. Let's go ahead and check our work. And, oh, what the heck? There's one more answer, or one more question up here. You know what? I'm going to leave that one to you. I'm going to finish right there. I'm going to say that's correct, and I'm going to call it a day. So that would be 5.2, day number 2. Have a good one.